Number 32 is a static equilibrium problem. And what we have is we have a long beam here that has a fulcrum in the middle. We have a cat sitting on this end. Here's our cat right over here. We have a cat here at some distance d. And we have food out here at this distance here, where this distance is 2 meters. This distance is also 2 meters. All right. So this is the cat on this end is 5 kilograms. The bowl of tuna fish on this end is 2 kilograms. Right here. And the seesaw is 4 meters long. What we want to try to find out is this cat right here, yeah, that doesn't look like a cat, is walking out here. We want to know how far the cat can walk out before the whole thing tips over. All right? Or essentially, how far can the cat move so it's still balanced? The cat, this cat here is a 4 kilogram cat. All right, in this case, we have a rotation point already defined for us right here. So we're going to draw our free body diagram. I'm going to try to do a better job here. So the cat over here is going to be mass 1 cat times g. That's the 5 kilogram cat. So this is mass 1 cat. This is mass 2 cat right here. Well, our rotation point is going to be right here. And then we have m2g. At some point here, we don't know that distance. That's what we're trying to find, is d right there. And then we have here, we have the tuna fish, which is m3 times g right here. And it's out here at this far point. We also have another force. We have a normal force coming up from the fulcrum right in the middle. And that's what's holding the whole thing up, both all the cats and the bar. And since the bar also has a gravity on it, but it's exactly under the fulcrum, we don't have to worry about that as long as we use this as our rotation point. So I'm going to do that the net torque about this rotation point. So then I look over here and I say, okay, this one on this side, M1, is making it go in a clockwise direction. So this becomes the force, M1G, times the distance it is away, which in this case is 2, times the sine of the angle. The angle is 90, but notice it's going clockwise, so this should be negative. And this is sine of 90. And then this one here is making it go counterclockwise, so we got plus m2g. Its distance away is d. It's also the sine of 90. And this one's also making it go positive, so this is plus m3g. And it's at a distance of 2 meters, and it's also at the sine of 90. So those sine of 90s, those all go to 1. And the net torque has to be equal to 0 for static equilibrium. So let's rewrite this. 0 is going to be minus m1g times 2, plus m2g2, plus m3g2. Okay, now look, we can divide by g and all the g's go away. And then we're going to solve it for d. So we're going to move this over. So this becomes, I'm going to make this 2m1. And then I move this over, it's going to be minus 2m3 is equal to m2 times d. Or d is going to be equal to 2 times m1 minus m3 over m2. Well, we have all those numbers, so this is going to be 2 times m1, which is 5, minus 2 over 4. So we end up with d is equal to 1.5 meters. And that's your answer. All right, that was number 32.